Our next section, inequations and inequalities. There is a subtle difference between the two, although we do very often use the wrong name for the wrong one. It's not that big a deal, but technically an inequation is when we're actually trying to find the values of something. So a problem where we're trying to find possible values, we solve it just like an equation, and we end up with a pronumeral being the subject of that. So x is greater than or x is less than. Technically that's an inequation. So 5x plus 3 is less than 2, not exactly the most mind-blowing of one, but just to use it as an example, and we solve it, and we end up with x is less than minus 1/5. Quadratic inequations. Let's have a look at these. We know how to solve a quadratic equation. Well, multiplies together to give the last number, adds together to give the middle number. In this case, 6 and -1. Now when it's an equation, no drama. We go, oh well, either x is equal to -6 or x is equal to 1. We can't do the same thing with an inequation. We can't just simply say, oh, either x plus 6 is less than 0 or x minus 1 is less than 0, because that's not true. So we have to think about it a bit differently. We can think of it graphically. I think, well, if I was to draw this quadratic, I know the x-intercepts are going to be those two main points, minus 6 and 1. In this case, they wouldn't be included in our solution. And we talk about a parabola, and we're basically saying, hang on, for what values of x is this parabola negative? And the answer is, well, the ones below. But of course, I'm not interested in the whole curve, I'm only interested in the x values. And so graphically, there's my solution. We're in between minus 6 and 1. So minus 6 and 1. I guess another way you could do it, the boundary points again are key. With a quadratic inequality, you're either going to be in between those 2 points, or you're going to be on the outside of those 2 points. So you could just test the number and see whether it works or not, whether it's included. In this case, 0 is always an easy number to pick, so I might pick 0, and I just sub it in and go, -6 is less than 0. Oh, yes it is. So 0 must be included in my solution. So I'm in between minus 6 and 1. Okay, let's have a look at this one. I don't know about you, I don't like negative x squareds. So I'm going to change it. X squared plus 3x minus 4. But of course, if I change the sign, I change the sign. So it's greater than or equal to 0. Multiply this -4, so we get plus 4 minus 1. So again, I can think of it graphically. Okay, well, there's my key points. Minus 4 and 1. Drawing my parabola. This time we're saying, when is this parabola above the x-axis? So this time I'm on the outside. Or again, I could just pick a point. 0, quite convenient. 4 is less than or equal to 0. No, it's not. So 0 is not included in the solution, so it must be on the outside of -4 and 1. So 2 possible ways you could do it, via a picture or via a substitution. Okay, so as I was saying, the solutions for a quadratic inequation will always be I'm in between the 2 numbers, or the 2 solutions, or I'm on the outside of the 2 solutions. Now, here comes a very special type of inequation, one where we have a pronumeral in the denominator, which of course causes problems, because we know the bottom of the fraction can't equal 0. So 1 on x is greater than or equal to 3. The temptation is to just turn both sides upside down and get the solution. What will we get? X is less than or equal to a third. However, that's not correct. So how do I approach these? First thing I do, because remember the denominator, that's what's basically causing me the problem, is I find where that's equal to 0. In this case, that would be x equals 0. So I know it can't equal 0. Then I just solve it like an equation. What I'm basically doing is trying to find those boundary points again for the solution. So I'll solve the equation. 1 on x equals 3, and there's that x equals 1/3. They become the 2 key points, or the 2 critical points. I'm going to do a visual way of doing it. I mean, there's my number line. I know naught's not included. I know 1/3 is included. And again, I'll just pick a point. What number shall I use? I actually chose -1. So -1, is -1 greater than or equal to 3? No, it's not. So I know I'm not on the left-hand side. I chose a quarter as well to test something in the middle. 1/4 is 4 greater than or equal to 3? Yes it is. So I know I am in between. And let's just confirm it. Let's check something on the right-hand side. X equals 1. 1 is greater than or equal to 3. No, it's not. So there's my solution. I've got the picture right there. So my solution is x is in between 0 and 1/3, including 1/3, but not including the 0. Now I think that's probably the simplest way of solving these questions. There is another technique, and I believe they use it in our textbook actually, where they multiply by the square of the denominator, and you end up with a quadratic inequation to solve. I just think that's too much work. Why make life hard for ourselves? Let's try another one. 2 on x plus 3 is less than 5. All I do is, bottom of the fraction can't equal 0. Okay, there's one of my key points, -3, can't equal that. Now I solve it like an equation, and I get, eventually, there it is, -13 on 5. So they're my key or my critical points. All right, in this case, neither of those points are included, because it's just a less than. Let's pick some points. Let's start on the right-hand side. 0, does that work? 2/3 is less than 5.
No.
Yes, it is. Yes, it is. There's a few people go, no, actually it is. So, yes, we would be on the right-hand side. A point in the middle of -13 on 5 and -3. How about -2.9? We can sub that in. 2/3 minus 2.9 is 0.1. 3 is 2/0.1. It's not going to be less than 5, is it? So no, we're not in between. And let's pick a number this side of -3. Any number you like. -4? Okay. Oh, that's a good choice. -4 plus 3 gives us -1. So 2 on -1, -2 is less than 5. Yeah. So it looks like we're on the outside for that one. And so there's my solution. X is less than -3, or x is greater than -13 on 5. So what's the difference between an inequation and an inequality? Well, technically, an inequality is a problem I'm trying to show is true for a given set of values. So an inequation is where we're finding the set of values it's true for, whereas an inequality is where it's saying, hey, prove it is true for these set of values. So they give you the set of values and you go to prove it. It's a technical point. As I say, we often use the wrong word for the wrong one from time to time anyway. It's basically like an identity proof. So when we come to proving things like inequalities, this is important. After you state what you're trying to prove, so you can rearrange what it is you're trying to prove. However, once I have decided this is what I'm going to prove, it's not an equation. It is not something I can move from side to side, because this is what we're trying to prove is true. Now, if I add things to both sides and things like that, then I'm assuming what I've got is true. So if I'm trying to prove something's true by assuming it's true, well, yeah, it's going to be quite easy to do. Can't do that. So let's have a look. Techniques. Sometimes, if you want to prove the left-hand side is less than the right-hand side, you can start with the left-hand side, just an algebraic expression, and play around with it, and hopefully show it's less than the right-hand side. You could move everything to one side. This is a common idea, because often it's easier to show something's always less than or greater than 0. So instead of trying to show the left-hand side is less than the right-hand side, we manipulate it and say, no. Instead of doing that, I'll show that the left-hand side minus the right-hand side is always less than 0. And that tends to be easier sometimes. Or I can start with the left-hand side, manipulate it to a new left-hand side. I might get stuck and go, oh, not quite sure. So then I go and work on the right-hand side and then manipulate it to be the same thing and go, oh, hang on a sec. And from there I can draw a conclusion about the two, that one is always less than the other. So new left-hand side is less than the new right-hand side, therefore the left-hand side is greater than the right-hand side. That's the basic idea in that one. Starts with something we know. They've told us some information. They've told us x minus y is always greater than y plus z. That is a fact, so we can use that. We have to prove y is less than x minus z on 2. Well, I know this is a fact. Now, if it's a fact and I know it's 100% true all the time, I can move terms. Because I'm playing with something I know to be true. This is true. So I'm going to move the y's to one side and everything else to the other. So I only can do that with known facts. If I know it to be true, then I can move things around. Now I'll divide both sides by -2. And if I change the sign, I change the side. And I've proven that y is always less than x minus z on 2. So in that case, I can manipulate because I started with something I knew to be true. I say one of the common ideas, move everything to the left, show it's always greater than 0 or less than 0. So what do we know? We know a is a positive number, b is a positive number. We're going to prove that ab outside of a squared plus b squared is always greater than or equal to 2a squared b squared. So what I'm going to do is go, no. I'm not going to do that. I'm going to move everything to the left-hand side, and I'm going to attempt to prove this is greater than or equal to 0. So let's see what I've got. Well, if I expand that out, AB outside of A squared, the second parenthesis is a perfect square. We know A is greater than or equal to 0 because we were told that. We know B is greater than or equal to 0, we were told that. And something squared, that's always going to be greater than or equal to 0. So yes, indeed, this expression here is always greater than or equal to 0. But I now know that to be true. This is now a known fact. So I can move terms. So therefore, I can get this -2a squared b squared, move it to the right-hand side, and that must be true. So AB outside of a squared plus b squared is always greater than or equal to 2a squared b squared. Keep in mind when you're playing with these sorts of things, squares are always positive or 0. A, B and C are positive. We're going to show that a squared plus b squared plus c squared is always greater than or equal to ab plus bc plus ac. I'm going to start with a known fact. I know that a minus b all squared is greater than or equal to 0. That's a fact. So I can play around with this one and manipulate it. I'll move the 2ab to the other side. So a squared plus b squared must always be greater than or equal to 2ab. Okay. A and B are just random letters. I could have done it with A and C. So if a squared plus b squared is always greater than or equal to 2ab, then a squared plus c squared must always be greater than or equal to 2ac. But hey, I could have done it with b and c. So b squared plus c squared is always greater than or equal to 2bc. If I now think of these as 3 simultaneous and add them together, I get 2a squared plus 2b squared plus 2c squared is always greater than or equal to 2ab, 2bc, 2ac. Divide everything by 2, and there's my result. So those 3 things that we looked at, the first one were the basic inequalities and quadratic inequations. Let's probably tune it. Pronumerals in the denominator is extension. You don't see those sort of inequations in a tune-it paper. Playing around with these inequations, now we're starting to talk extension too. sort of level of stuff. So that's a little taster for those who end up doing extension 2. But have a go at it. Don't let me scare you off it by saying, oh, that's extension 2.